So we have two transformations here. We could either reflect it over the x-axis, or we could do nothing. We could leave it where it is. And we need a name for that. And let's call that 0, or the identity, or the do-nothing transformation. And we also need to talk about operations. And the operation here is going to be one followed by the next. You do one transformation, and then you do another transformation, and you see what the net result is. Interestingly, in mathematics, they actually call that composition. It's compositional transformations. So let's look at this geometrical transformation. We have two transformations. We have the do-nothing transformation, and we have the reflection transformation. And what we're going to do is one after another. If we do nothing and then do nothing again, the net result is doing nothing. If we do nothing and then reflect, then the net result is just a reflection. If we reflect and then do nothing, we just get the reflection. But if we do a reflection and then reflect again, the net result is just the do-nothing transformation. The end result is the same as if we had just done the single transformation, do nothing. So now we have two transformations. We have a set of transformations, just two of them, the do-nothing, the identity, and the reflection. And the operation is doing one followed by the next. We can actually write out what's called a group table. It's an array listing all of the possible outcomes from this operation. Now for us, we have two transformations. We have two inputs and two inputs for the other one. That gives us outputs that form a 2x2 table. Now let's look at some functional transformations that are actually really similar. If you take a function, you might graph it, but you might just think of it as a function, like f of x. And the identity transformation would be to do nothing. But we could also do a negation. We could take f of x, and instead of just leaving it as f of x, we could look at negative f of x. If you're thinking about this in terms of the representation of the graph, it actually flips the function over the x-axis. And so now we have two transformations on functions. We have the do-nothing transformation, leave it the same, or the negation transformation, where you put a minus sign in front of it. Again, the operation is composition, so we could do nothing, and then we could take the negation. Or we could take the negation and then do nothing. Now, of all of the four possible pairings, only one of them is really interesting. If we take the negation and then the negation again, we get back to the identity. We get back to the do-nothing. Graphically, that would be if we flip it over the axis and then flip it again, we're back to where we started. Now, as before, the do-nothing transformation is the identity. And as before, the negation is its own inverse. That's the one where if you negate it and then negate it again, you get back to the identity, the do-nothing transformation. Again, I want to be clear, the transformations here aren't the graphs, but it's how the graph is changing. The transformation isn't the picture, but how the picture changes. Let's look at a numerical example now. Let's think about addition on odd and even numbers. Not the individual numbers, but let's think about the set of the evens and the odds. So we just have two things in our set, all the evens and all the odds. The operation we're going to work with here is addition. And we can construct a group table for this. If you take even numbers plus even numbers, you get even numbers. If you take even numbers plus odd numbers, the result of any one of those is going to be odd numbers. If you take an odd plus an even, you get odd. And finally, if you take an odd plus an odd, you get even. The identity here is even, because it operates on all the other elements without changing it. If you take something and add an even, you get that something back again. If we think about inverses, both evens and odds are their own inverse, because again, we figured out that even is the identity. And so you're asking the question, if we have an even, what should we add to it to get an even? And the answer is an even. If we ask that question with an odd, if we have an odd, what should we add that to? What should we add to that to get an even? The answer is an odd. Let's look at another way to write this. Mathematicians call this group Z2, and we think of it as addition modulo 2. What you should really think about is, if you divide by 2, what is the remainder? Because the remainder is always either 0 or 1. And 0 if it's even, it's 1 if it's odd. And so, when we write it this way, 0 sort of stands for all of the even numbers, because you always get a remainder 0. And 1 sort of stands for all of the odd numbers, because that's always the remainder when you divide by 2. When we construct a table for that, it looks like this. And the only thing that looks weird in this table, that's not sort of the standard addition we know, is that 1 plus 1 is now 0. And that's because 1 plus 1 is 2, but the remainder when we divide by 2 is 0. And that's why 1 plus 1 is 0 when you're looking at Z2. Now in this particular group, the identity here is 0. If you take anything and add 0, you're going to get that thing back again. And again, each one of these elements is its own inverse. 0 plus 0 is the identity, 0. And 1 plus 1 is also the identity, 0. Let's turn to a musical example now. We could have no change in a melody, and that would be the identity transformation. Or we could do the inversion, what we heard earlier. So here's a melody, and this is a melody we're going to talk about a lot today. So that's a nice melody. If we invert it, here's what we get. And we can think about this as a group, because now we have two transformations. We have the do-nothing transformation, or this inversion. And now the operation here is to do one after another, and we can look at the structure of this group. We can figure out what its table looks like. Now we need to remember that we're not looking at the melody itself. We're looking at how the transformation changes this melody. So let's construct this table. Now some of the outputs are obvious. If you do nothing and then do nothing, you've done nothing. If you do nothing and then an inversion, that's just an inversion. A little bit trickier is if you do an inversion and then do another inversion, you get back to the identity. You get back to the do-nothing transformation. Now you've probably noticed that all the group tables we've looked at, they're all very similar. Mathematicians would say they're all copies of Z2. They're they're all what we would call isomorphic. Before we get to more of that, let's look at how composers use musical transformations when they're composing music. In particular, we're going to talk a lot today about Bach and how he used these transformations. The piece that we're going to talk about today a lot is Johann Sebastian Bach's 14 Canons on the Goldberg Browning. 14 canons. So these are 14 individual pieces. The 14th canon is actually what we played at the beginning of today's lecture. The number is BWV 1087 in Wolfgang Schmiede's system. These were not found until 1974. A copy of these 14 canons was found in an original copy of the Goldberg Variations that Bach owned at one point. We know that they're actually Bach because a couple of these canons appeared elsewhere before them. Now these are some of the really brilliant fugues and canons that Bach wrote that have incredible mathematical structure to them. So there are these 14 canons, and each one is compactly written using transformations. These are simple yet beautiful. I think the proper way to view these is that some of the early ones especially, are sort of studies, where Bach is studying this simple melody and figuring out how to use it, how it fits with itself in different transformations. And those are stepping stones into more complicated canons. And throughout the 14 canons, every once in a while, there's a much more complicated canon, which is more like what we think of as beautiful, complicated music. But I think because of this, we actually get a lot of insight into how Bach put puzzle pieces together and how he used transformations